So that makes it a little hard to deal with because the syntax in a synthesizable module that, for instance, you're going to be testing this week in Lab 1 is not the same as the syntax in a simulation module, which will be the test bench that you need to write to test your module. So the test bench is going to be non-synthesizable Verilog. It is, after all, a test environment. But the code you're testing has to be synthesizable. There's a variety of stuff online. I particularly liked Evans and Sutherland's standard gotchas, ways you can shoot your own foot off with Verilog, and all nicely laid out. Perhaps the most, well, implicit net declarations. I can't begin to tell you how many times I forgot to declare a signal, and signals by default in Verilog become nets of width 1 with no error message. And if you use them in any other way, then you throw an error or you get an undefined result. So that has implications we're going to talk about a little bit. Number bases are interesting. Literal numbers are 0 extended. This one, though, operation of sign and sign extension. I went through this slide. You might want to do this. I went through this slide and read the description and then tried to come up with the answers they say that you're going to get under 3 different conditions, all of which are different for an addition. And I couldn't do it until I looked at the next slide. So you might want to see if you could do that. Operation on size with size and sign extensions. There's a lot of mathematical subtlety here. There's various synthesis-oriented tutorials and pages, and some other information. And oh, by the way, Cordes Prime does support System Verilog if you want to write in System Verilog. But the basic construct that you should think of in Verilog is that you're assigning voltages to wires. You're not assigning bits to memory like you are in a programming language. You're assigning logic levels, or voltages in other words, to wires. Wires don't have memory. They don't remember a voltage on them. It has to be continuously assigned to a 0 or a 1. Furthermore, every wire can change voltage at any time, not sequentially, not in any order, all of the time and at any time. And third, let's say, I lost a pointer, got a dangling pointer. A wire is lost it. Okay, never mind. But this implies that the language is inherently parallel. That's what I was going to say. And every assignment statement happens all the time. There is no sequentiality. And C is sequential because somebody built a state machine that enforces a fetch execute sequence of events. You can make the FPGA sequential by writing your own state machines. And that is the only way, writing an explicit state machine is the only way of making sequential operations. For loops are not sequential. While loops are not sequential. For loops, instead of being sequential, produce a list of hardware, all of which is elaborated at compile time and exists for the rest of the time that the code is running. So there is no sequential implication because there's no clock unless you put in a clock.
Okay, so what happens when while loops are statically elaborated?
While loops, you make copies of the hardware in the while loop. Same with the for loop. Therefore, that implies also, by the way, that while loops and for loops have to have finitely defined boundaries, non-computed boundaries. They have to be explicit boundaries because they have to know how many copies of the hardware built. And once again, Verilog code is mapped to actual gates, not bit strings in memory. So timing is determined by physical hardware. In simulated Verilog, there is a construct which says how many clock ticks should go by between statement executions. In synthesizable Verilog, there's no such thing because there's no clock unless you apply a clock. Module invocation in C, if you invoke a function and you're implying that you want it executed. In Verilog, if you define a module, invoke a module, it implies building the hardware connections, not doing any kind of execution. It's not a function call, and that implies that you can't instantiate a module. You cannot instantiate a module in an always block because that would imply that you're building infinite hardware at runtime. Not a good idea. Furthermore, syntax has hardware consequences. Each plus sign instantiates a new adder. Therefore, you can change the order in which additions are done by changing the syntax. Putting brackets around a plus will change the hardware that's built. So if you have A plus B plus C plus D, you'll build a single adder with a single level that adds four numbers together. On the other hand, if you do this, you will build an adder, another adder, whose results are added together. It may be faster to do that and use less hardware. Each multiply in Quartus compiler, each multiply uses one digital signal processor block, unless you suppress that option with a compiler directive, which I'll talk about in a minute. So the syntax, the adding the little star syntax which implies multiply, actually uses hard IP on the FPGA. As I said, loops build copies of hardware. If you find that you're going to have to use a loop to build hardware, then I strongly suggest using a generate statement, which we'll talk about before in lab 2. Use a generate statement to control looping because it gives you better flexibility. In lab 2, you'll need to build copies of hardware. You might need to build 500 copies of a small CPU. And it gets tedious to do cut and paste. Conditional assignments, if then else, or case statements, have to be complete. There can be no missing cases. Why? Because a wire cannot be in an undefined state. It can't have no voltage. It's going to be driven 1 or 0. And a wire has no memory. Therefore, if you're asking for if you write a piece of code that looks like this, if C equals 1, out equals in, what if C is not 1? What does out equal? What does it equal? The only thing that makes any sense at all is that it matches the last thing that you assigned. Therefore, you have implied memory. You've built a latch. It's not a asynchronous latch. That means it is impossible for the timing analyzer to decide whether the design is correct or not. Don't do this. Always check the warning list for inferred latches, because it's impossible to follow. Furthermore, there's no standard word sizes. Yes?
Is there a compile flag we can set so that just won't compile with inferred latch?
There is no compile flag for inferred latches. There is for default net types, but not for inferred latches.
But that's important.
I agree. There is, every once in a while, you'll want an inferred latch. But in your designs, you're never going to want it. I've come across one design, I can't remember what it was, that required an inferred latch. There's no standard word sizes. It's not like you have car, short, ints, and long ints. You can make any number of bits you want. You can have 1 bit to several thousand bit words. If you do an add on a several thousand bit word, of course, don't expect it to run at 100 megahertz because it uses a ripple carry. But you need to specify the width of every wire register literal. Otherwise, you will have unusual, sometimes hard to debug results. Literals which are not specified are considered, if you say A equals A plus 1, then the 1 defaults to 32 tick decimal 1. So it is a 1 of width 32. Probably not what you want usually. Generally speaking, signed arithmetic has to be handled very carefully. And you can get into all kinds of edge cases where you mix additions of signed and unsigned variables of different widths, and you will get results that make no mathematical sense because it's doing very literal bit manipulation when it's doing the add. So determine the width, set the width of all signals. There's so much, there's a lot of chit chat about this. There's a whole bunch of different things you might want to read on the pitfalls of signed arithmetic. Obviously, you're going to have to do signed arithmetic, but you have to do it carefully. Cyclone 5, in fact, Quartus has no automatic support for floats. There's no float type. There's no real type. But you can always write your own floating point. It's just another module. Had a student who did it. I cleaned it up and extended it slightly. You can use it if you like. It works. It's fast. There are actually four values for a wire. A wire could be a 1, a 0, a don't care, or a high impedance. And there are very few cases. Real wires can only take on values of 0 and 1. Don't care and Z. Oh, don't care means nothing in this case. It means, what don't care means is, if you do a comparison, just don't include that bit. It doesn't mean the bit has a bad value or an unknown value. It just says, don't bother to look at it. Z, high impedance, does have a specific meaning in synthesized Verilog, and that is that you are specifying that you want a tri-state gate. You know what that is? Everybody knows that? Remember what a tri-state buffer is? So, if you're saying that you're floating the output of a tri-state buffer, then you can have a value of Z for the wire. What that means is not that the wire has a value of Z, but that you're jerking the control line on a gated buffer, so that so the input, no matter what the value of the input line is, 1 or 0, the output of the line is just floating. Cyclone 5 does not have tri-state any place except I/O pins. It's the only place you absolutely have to have tri-state to run a, say, memory. So it exists, but don't use it except on outputs. Now that being said, here's a case of using a case statement in a don't care. I wanted to find where the position of the leading one is. And so I wanted to do a comparison where I cared where the leading one is, and then everything to the left of it was zeros, but I absolutely did not care what the values to the right were. Because all I cared about was the position of the leading one. And in that case, a don't care in the comparison makes a lot of sense. When you do that, you better use case X and not case. And you notice that just to make sure I didn't leave a case out, I have default here. Putting in a default in the case statement ensures that you will never generate an inferred latch, because it will always be true if nothing else is. You can store stuff in memory if you build a memory. The Cyclone 5 has a few hundred memory blocks that you can infer directly from standard Verilog. And then you have to, of course, build a memory controller that says, here's how to manipulate the I/O lines for the memory I've just built. If it's SRAM state 0, we set up everything, we wait a cycle, we ask if we're doing a read, do the read, if we're doing a write, do the write, go back to the beginning. So you have to build a state machine that has a minimum of 2 states to handle a single access memory. Typically more than 2 states, but you have to build the state machine. Oh, I remember what the last thing was for a wire. Each wire register can only be assigned at one location in a Verilog design, because if you assigned 2 different values at 2 different places, you'd be effectively hooking together 2 outputs to 1 input, and you're not allowed to hook 2 voltage sources together. Bad idea. Draw a lot of current. So every variable has exactly 1 assigned statement, or is defined in 1 always block. If you statements within an always block can do multiple assignments to a given variable, to a given signal, because when you do that, you are actually inferring a multiplexer within the always block. Yes?
Okay, here's a question about that. Let's say you have an always block and you use this structure. Assign x equals y. If some condition is true, assign x equals z. Does that correctly infer a multiplexer, or does
Yes.
that infer a latch?
It infers a multiplexer if you do, yes, it infers a multiplexer.
Okay.
So here's an example. If function add ALU equals, no, it actually latches unless you have it complete. If ALU equals add, or if it's functions add, you get A plus B. If functions add, you get A and B. Otherwise, you get 0 out. And that is not a sequential operation. It doesn't choose one or the other. It does all of them and chooses an output through a series of multiplexers. So what you're building from this is this structure here, is this circuit. If the if were incomplete, it would build a latch into that. You don't want to do that. Now, just to make things extra confusing, unlike C, there are two different operators that both do an assign to a signal. Blocking and non-blocking. Non-blocking designs are indicated by the left arrow equal operator, and you're going to, without fail, use this in every clocked logic always block. And I'll show you why in a minute. Without fail. Blocking assignments are indicated by the equal operator, and you're going to use this in all combinatorial blocks without fail. These are non-clocked always blocks. Because it allows you to set up a logic structure as a series of what appear to be sequential lines. But they're not sequential in execution, merely they infer a priority encoding. So they produce a multiplexer, but they do it in an order which is dependent upon the order in which you put the operations. So let's just compare an example here. So this is blocking versus non-blocking, and it's a positive edge clock, so it's a clocked block. All of this is the same. We're setting up three intermediate signals. We're setting up an input and an output from the third flip-flop, so to speak, a clock signal. And then we're saying Q1 equals blocking D, Q2 is equal to blocking Q1, Q3 is equal to blocking Q2. And what is generated by this code is an input that goes directly to Q3, because Q1 is sequentially connected. D is connected through Q1 to Q2 to Q3, so all you need is D and Q3. On the other hand, if you put a non-blocking assign in here, it says do all of these operations at the same instant. These are parallel operations, truly parallel operations. At the same moment, you want D to be assigned to Q1, Q1 to be assigned to Q2, Q2 to be assigned to Q3, and in that case, you get a shift register. What do you actually want to build? That's what you have to ask yourself whenever you have to decide on blocking versus non-blocking assigns. Question? Any questions? I particularly like this example. Always at positive edge clock begin, y equals x, x equals y. What does that infer? A wire. On the other hand, if you use non-blocking, then you get a set of interlocked flip-flops that swap values. Because on the clock edge, x gets copied to y, and simultaneously y gets copied to x. Here, syntactically, y gets a copy of x, and then y is copied back to x. Oh, x equals x. Any questions? What do you want to build? You have to ask yourself what you're building, because it matters. Here's an example of a combinatorial where we're gonna add two values. We're gonna add another two values. Then we're gonna add the two parts, and we get a hierarchical adder inferred because these parts appear syntactically before this part. That implies sequentiality, but it is not sequential. They're There's no clock. There's no sequencing through statements. It specifies the shape of the logic, of the combinatorial logic which is built. Pay attention to warnings. Now, this gets a little tedious when there's 600 or 1,000 warnings. Do it anyway. There's a search function on the warnings. Do a search for inferred. Do a search for implicit net, unless you use the command backtick default net type none. That sets the compiler option to no default net types, and therefore to throw an error when you have an undeclared variable. The real killer, which I've done by the way, is to declare a 1-bit reset and then misspell it in here. And the result is this gets inferred and never changes. And the system never comes out of reset because it's active low. It defaults to 0 value. And the system doesn't execute. In fact, it's worse than that. The CPU that you've just built gets optimized away because it can never execute. You say, wow, that was really efficient. That CPU didn't take any logic at all. And I've gone through that thought process, and then when you see that, you say, wait a minute. But the sad thing was I actually had to go through that process. And again, read the synthesis report to make sure that you actually use the number of DSP blocks and memory blocks you think you should be using. You can guess how many multiplies there are in your design, and you can guess about how much memory you're going to use. Make sure that the report says you actually used that memory. And it is possible. There's at least 4 kinds of memory on this particular FPGA, and if you don't specify exactly what you want, the compiler may infer the wrong kind of memory. Or for instance, you think you're using M10K blocks, which is bulk hard IP memory. But in your code, you accidentally specify that you want global reset line on the memory. Well, M10K memory does not support global reset. And so the compiler says, that silly user must want to do the memory in random logic. And it builds it in random logic and uses all of your logic. So, I guess the terse summary is you got to think about what you're actually building. Because this is a hardware inference language, not a software language. Any questions? Anybody got the solver running in simulation? Any questions about the solver from last time? Video is up, thanks to Josh. So you can go back and look at that again. It's up on YouTube. Well, let's talk a little bit about that if there's no questions. Usually setting up a test bench. So the example I used to test my understanding of testing was to build a direct digital synthesis unit, which is a simple piece of code which generates a sine wave. And it does it by incrementing a phase accumulator. And for those of you that have been through 4760, I beat this to death at 4760, but doing is you're mapping the phaser 0 through 360 degrees onto the overflow of a register, in this case, a 32-bit accumulator. So we're going to map this onto the region 0 to 2 to the 32. And every time the register overflows, we're going to output a new sine wave cycle. So what I wanted to show was that I could run this, and I preferred not to run Model Sim from the Quartus environment, but rather to run it from the command line or from as a standalone. So this is the directions for running Model Sim as a standalone program, which then, when run, outputs the sine wave as an analog entity from the direct digital synthesis. And what I'm going to ask you to do for lab 1 is, instead of a sine wave, to put out the X1, X2, and X3 signals from the solver to show that they approximately match the MATLAB waveforms. So you're going to want to read this page. Then the second part of the assignment is to export the data from Model Sim to MATLAB. So you're going to want to read this. Export 3 vectors to MATLAB. 3 vectors to MATLAB, X1, X2, X3. And then plot the data as a 3-dimensional phase plot, not as X1, X2, X3 versus time, but X1 versus X2 versus X3. Okay. So this page has the information you need to do that. And if you're looking at this from the top page for the course, Verilog summary is here. That's what we've just been talking about. And if we go down to verification, using Model Sim is there. And if you want to get a little head start on it, you can start reading about my lovely homebrew logic analyzer, or about on the Quartus Prime compilation page, there's a section on using signal tap, which is the on-chip logic analyzer that Quartus defines. So around about Wednesday, I'm going to take the net IDs of whoever's left in the class, and 2 or 3, I guess 3 or 4 people have dropped, not too many. But take whoever's left in the class and send those off to give you door access. So you'll have door access probably by the end of the week. On Wednesday and Thursday in lab, we will set you up with hardware, get you an SD card, expect you to format the SD card, get it ready to execute while you're demoing your results from for the week 1 checkpoint, which is all simulation. So there'll really be 2 things to do. One is to get the hardware set up and running. At the same time, you're demoing, but you have a couple of people usually in the group, so that works out. So any questions at this point? Well, in that case, let's talk a little bit more about VGA. So, week 2, yes, week 2, checkpoint has 2 parts. The first is to either demo signal tap or OLA connecting your solver to debug and display the 3 solution variables. And also to have the HPS, the ARM CPU, draw plots for this ODE solver on the VGA. And so we need to talk about the VGA subsystem now as a QSys entity and as a logical programming device. And this is linked in Lab 1, but where you're going to find that is in the so-called University Computer page, which was where I plowed through a lot of stuff while I was trying to figure out what worked best. And what I normally do is I do a bunch of examples, and then when I finally get one I think is stable, then I invert the order of the page, because nobody ever reads past the first example on the page. You're all used to reading blogs, and so you read the first example and you stop, because that's the latest example. And so I haven't inverted this page yet, so you have to go all the way to the bottom. If you handle that. And, or most of the way to the bottom. There's actually some details below that. But the simplest to use, the best worked out, the simplest QSys is the VGA 640 by 480 resolution displayed from SDRAM, 16-bit color. And for reasons that escape me, the default computer system which ships from Altera, Intel, excuse me, displays partly from SDRAM and partly from onboard memory, from SRAM onboard. And it's just unnecessarily messy to set up. So I simplified it. We're displaying 640 by 480 from SDRAM. It's no big problem because after all, you can only display 1 pixel at a time. And so the fact that it is sequential single access memory doesn't matter. And it's big, so you can put several images in memory if you want and switch between them very quickly. But it uses SDRAM as a frame buffer. It also allowed to go to 16-bit color rather than 8-bit color. And in this case, the top level Verilog does only one thing, and that is that it connects the QSys generated module to the I/O pins. So there's no actual Verilog logic. It's all intellectual property. It's all IP that came with the computer system. But the top level QSys looks like this. So this is the bus abstraction we're going to be using. And always at the top of this is going to be some clock, in this case a phase lock loop, which is bumping the frequency up to like 875 megahertz. There's the ARM, which I think I talked about a little bit last time. It has a whole bunch of interfaces, including a AXI master and a lightweight AXI master. And you're going to be using the lightweight AXI master and the AXI master to send commands to the lightweight master and data, pixels, through the high-speed master, through the full master, to a location in SDRAM. So the AXI master is now off screen. We'll bring it back on. So the AXI master here. Still, that's off the top. Yeah, there we go. Maxi Master goes down here and it drives the slave 1 port of SD RAM, which is also driven from another place, which happens to be another master, which is the VGA controller. There's also associated clocks and resets. But this allows us to read and write all of SD RAM on the FPGA. You can also read and write on-chip SRAM. I typically put 1 block or so of SRAM on most of my designs because I like to use it as a scratch pad between the HPS and the FPGA. Gives you 256 words of memory. You can just write anything into for I/O. So then the VGA subsystem is going to have 2 inputs. There's a character buffer control from the lightweight master and a character buffer slave from the full bus for writing characters to the screen, because you'd like to be able to put text on the screen and it's tedious to draw it yourself. And then the Pixel DMA address controller goes back up and also touches SD RAM. Now, so what happens if the VGA controller and the ARM both ask for SD RAM access at the same time? Because there could be contention. Well, you can break the system by writing enough pixels per second from the ARM to the across the bus to the point where the VGA controller cannot get enough cycles to keep the screen refreshed. VGA requires 25 million pixels per second when it wants the pixels. No fooling, it just wants the pixels. But the bus is running at 100 megahertz. It takes 1 cycle to read or write. So now you've got 4 cycles to play with to get that piece of data. 100 megahertz, 25 megahertz. And unless you really, and there's a FIFO built into the system. So unless you really load the system down with accesses from the HPS, more than about 7 million pixels per second. That's 15 frames a second with every pixel written. You're not going to saturate the system. I don't think you can write that fast. So you have effectively simultaneous access from the HPS and from the bus master, which is the VGA controller. There's a zip file down here which has the whole system zipped up in it, and you're going to want to download that probably as the general outline for Lab 1. This is going to be more or less the project that you're going to want to start with. You're going to have to add a bunch of stuff to it. For instance, in QSys, going back to QSys, in QSys, you're going to have to use a menu over at the side and add a few parallel I/O ports so that the ARM can control your solver, and so that the solver output can get back to the ARM. And all those parallel I/O ports are going to be bus slaves that are controlled by the HPS. you probably have to add, I don't know, 10 I/O ports. I/O ports are cheap. There's a bunch of stuff I had to do to make this work. I had to get down and grovel around inside the display system to get it set up for the right color and everything. But to do that, most of the rest of the logic is on the HPS, which I'll talk about next time. Unless, and of course, you might want to read up on that a little bit, since it's coming down the pipe at you in about 8 days. Any questions on this? You can draw lots of pixels per second on this system. Yes?
So if you're drawing something like the trace of the signal that we're going to want to put on the screen at the end of this project, would you just want to write that pixel by pixel?
So you could imagine, so the question, you want to write you've got these traces that you're going to produce, and you could imagine just drawing every pixel along the trace, and that's basically what you're going to have to do, although there is a line primitive that allows you to connect solution points together. But basically, yes, you're going to draw these pixel by pixel. Now, what happens when you get to the end of the screen? I think I said that you either had the option of scrolling the whole thing across the screen, which means rewriting lots of pixels. Doesn't mean rewriting the whole screen. It just means erasing what you've already drawn and redrawn. Or it means starting at the left-hand side, erasing a bar like this and rewriting here. And then continuously erasing a whole vertical line. Every time you draw a point, you erase another line. So you'll be erasing lines, which is only 480 points. That's negligible. And you're not going to do more than a few frames a second because your brain can't take it. You can't. I mean, none of you can look at dynamic systems at 30 frames a second and figure out what's going on. So the number of pixels you're going to write is going to be on the order of thousands per second. And you can write millions. So there's no problem with overloading the system. With this application. For lab 3, there will be a choke point, because in lab 3 I'm going to ask you to write millions of pixels a second. And in fact, the write rate may become a dominant part of the calculation time, to the point where you can't afford to write back to the HPS. But rather, your Verilog will implement a bus master that writes directly to the VGA yourself. And if you change the VGA around so it's not in SD RAM, but rather in static RAM on chip, you can do simultaneous 2-port access. You can get the write rate up to about 100 million pixels a second. Don't hesitate to ask, shoot any questions off to Piazza, and we'll get the, looks like Josh is taping the lecture, such an obsolete word, recording the lecture. So we'll get that up too. See you Wednesday.